Alright, hey guys, and welcome back to another AP Physics C Mechanics video. Today we're going to do the 2022 set 1, and then we're going to move on to 2022 set 2, probably, hopefully today, we'll see. So yeah, let's just get into it, read the first question. Okay, here we go. Alright, a block of mass M is pulled across a rough horizontal table by a string connected to a motor that is attached to the floor. The string passes over a pulley with negligible friction that is vertically aligned. So there's the pulley with the left edge of the table as shown. The string and pulley both have negligible mass. The pulley is at a height h above the table. I see that, and the motor exerts a constant force tension on the string. So force tension, or well, let's write force tension, and the block remains in contact with the table at all times as the block slides from x equals L to x equals 0. Okay, cool. The coefficient of kinetic friction between the table and the block is mu k. Express all answers in terms of mh, ft, x, mu k, and L, and physical constants as appropriate. Okay, cool. On the dot below that represents the block, draw and label the forces, not components, that act on the block when the block is at x equals L. So when the block is here, they want the forces that act on the block. Each force must be represented by this. Okay, well, that's just a free body diagram. So we know block is on the table. There is a normal force that is right now not necessarily equal to gravity because we have this other force tension, which has a y component, which will relieve the normal force of some of its duties to keep the thing from falling downwards. Because if you have like an upwards force, like, if you're lifting something off the table, the normal force becomes less and less. So this has to be less than this. And then we got force friction. It's moving this way, so force friction must be that way. I gotta write it the right way. Force friction, there we go. So force tension, friction, okay, gravity, and then gravity is because it's on Earth. So derive an expression for the angle theta that the string makes with the horizontal as a function of x. Okay, so let's think about our triangle. Here's x, here's theta. Here's h. H is always going to be a constant. And let's think about how do we get the angle theta. Well, angle theta, this is also, by the way, this is going to be, there's 3 different ones we can do. I'm just going to use one of them, which is most convenient. We're going to say that, use the Pythagorean theorem, a squared plus b squared equals c squared, and say this side is x squared plus h squared. Understanding that x squared plus h squared equals hypotenuse squared. And in order to get the hypotenuse, you would just take the square root of x squared plus h squared equals hyp. And that's where I get this thing from. So now I'm going to use trigonometry. So Katoa, sine, opposite over adjacent. Okay, so what's my theta? Okay, my opposite is hypotenuse. So sine theta equals opposite over, what was my hypotenuse? My hypotenuse was h squared plus x squared. And now in order to get the theta as a function of x, we'll do inverse sine of h squared plus x squared equals theta. And there. Now you could use cosine or tan. I'm just doing this to have it easier. So derive an expression for the normal force. You'll see later why it's easier because I needed to derive that anyway. So derive an expression for the normal force Fn exerted on the block by the table as a function of the block's position x. So the normal force exerted on the table, by the block on the table as a function of the block's position x. So we'll do our sum forces y first because we want to find a force. So sum forces y has to equal, well, the force normal, we'll call that. Did they give us our positive and negative? They did, right? Yeah, so positive y is up. So force normal plus Fty. Now Fty, I'm not including the whole force tension because obviously here there's some components. Here's Fty, excuse my handwriting, and here's Ftx, right? So I only want Fty to sum my forces on the y. I only want that component. And then minus Fg has to equal 0 because the block is not accelerating up or down the entire time. So now I can say that Fn, do some algebra, is equal to Fg minus Fty, right? and this is FG. Okay, well, FG is always MG, and they said we could use mass in our answer, right? And physical constants like G. So we're going to bring this over here. We're going to say Fn equals, right, mg minus, now what's force tension y? So force tension y here is going to be, let's think about it. If we want the sine of this angle, well, sine of the angle is also, I should write it down there. Sine of the angle was h over h squared plus x, or the square root of h squared plus x squared. But it is also ft, I think it's y, over ft, right? Because we had these components, and then we had ftx, that also make a triangle, and then ft, so it's opposite over hypotenuse, right? So this is also equal to sine theta. Oh, I'm an idiot, sorry. So if we, sorry, yeah, no, that's right. So if we wanted fty, we need ft sine theta, which is equal to fty, just rearranging, multiplying this to that side, right? So that's how we get fty, so we'll sub that in there, ft sine theta. So now we have fn as a function of sine theta and ft. But they wanted, I think we can use ft, right, as just the base. Okay, we can use that. We don't have to rederive it. So they wanted as a function of x, but we know sine theta as a function of, or well, we know sine theta right here as a function of x. So we're just going to sub that in so we can have the answer in terms of what we want, right? So we'll just move this over here, subbing in for sine theta. So we'll have mg minus ft, and sine theta was h over the square root of h squared plus x squared. And I'll just write here off in this corner equals ft. Or no, sorry, equals fn. Great, and now I'll box that up just to show the reader what my answer is. There we go. Ugh, and that's the answer. Just making sure it's h. It is opposite over. Okay. Nice. Next question. Derive an expression for the magnitude of the net horizontal force, just the net horizontal force exerted on the block as a function of the block's position x. Okay. So they just want some forces x. This is what they're asking for. So some forces x is equal to f net x. So let's think, what forces are on the x? Well, we had that other component, which is ft, and where was our positive? So our positive is this way. So ftx is actually going to be in the negative direction. So we had negative ftx plus, and then friction was acting in the positive direction. And that's about it, which is equal to this answer, which we want. So now we'll sub in, because we know that we want everything in terms of mu k and all of these things, but we can't leave it in terms of just ftx. No, we need ft, like cos theta in this instance. So the reason why we're going to find ftx. So ftx is equal to ft cos theta, because we want that other component, like in the triangle, right? Here's ftx, fty, ft, here's theta, and if we wanted cosine theta would give us ftx. Oh, this is really bad. Cosine would give us ftx over ft, and if we multiply ft to both sides, we get ft cosine theta equals ftx, right? So that's why we want ft cos theta. So now we're going to change this equation again. So we're going to say f net x is equal to negative ft cos theta. And now the force of friction, just by definition, is equal to mu k fn. But up here, we derived fn. So we can just sub that in. We don't even have to worry about that. So we'll say plus mu k, and we're allowed to leave it in terms of mu k. Like, that's what College Board told us. So this is going to be a long equation. So mg minus, I think it was minus, right? Yeah, minus ft, and it was h over the square root of h squared plus x squared. And we can leave it like that. So now we need to get rid of this pester this cos theta that they don't allow us to leave in terms of, because they said ft, m, and other stuff, not cos theta. We can't leave our answer with cos theta inside there. So we're going to understand that triangle again up here. So cos theta was equal to ftx over ft, but it's also equal to x over, well, by this drawing over here. Did I mess something up? No, yeah. Cos theta is also equal to, if we look at it, adjacent over hypotenuse. Oh, then cos theta has to be equal to x over square root of h squared plus x squared. And I'll leave that in parentheses. Forgive my handwriting again. And now we have everything in terms of how we're allowed to have it. Like we have everything in terms of m and all the other good constants and values that they give us. Sorry. And we'll just leave it like that. And there's our, it's a long answer, but I assure you, I'm pretty sure that's right. So there we go. So that's our answer. Write but do not solve an integral expression that could be used to solve for the work done by the string on the block as the block moves from x equals L to x equals 0. Okay, so work is a scalar. So we're going to think. So work y plus work x equals work string. Now you may be asking, well, why are you breaking it up into its components? Wouldn't it be just easier to use like f dot d, right? Now I could do that, but I want to acknowledge that the only work being done in this situation intuitively is on the x-axis, because this block has no no displacement up or down, so there's no point in considering the y work. So I'm just going to actually, you don't even have to write this equation. You just have to make this statement that work string y equals 0. Therefore, work string equals work string x. And now you can do your integral expression, right? So let's think about it. Well, work string x has to be the integral, and it says as it moves from L to 0, so there's our displacement. So let's do our bounds 0 to L. And now what was the x force? The x force, like we said, done by the string. So it's not the horizontal, like we're not asking for the work done by friction. No, just the work done by the string. So it'd be the integral of ftx, but now we also have to consider the direction, right? Because ftx was that way in the negative direction, so it's going to be negative ftx. And now we're going to write dx. So now we're going to bring that over here, right? Because we can't leave it in terms of ftx, we're going to write our integral. And if I didn't show that integral, if it cut off, there it is, right? Integral from 0 to L. And now let's recall ftx was negative ft cos theta. We're going to write dx. Okay, well, we're going to keep simplifying. We can take that negative out because it's a constant. It just bothers me. It's up to you. ft. Now, we remember cos theta was x over the square root of h squared plus x squared. Now we can write that dx, and now we have x here, x here. This is a solvable integral, so we can just leave it like that because they only wanted the expression. They said write, but do not solve, and there's our answer, right? Next question. Does the string do more, less, or the same amount of work as the block moves from x equals L to x equals L over 2? So does it do more when it's like, I'll draw this out, so when it's from here to here, or when it's from here to here? Right? If you can just visualize that, right? So we're going to think about this. When the string is, when the string's at its initial position, the x component of the force has to be the greatest because the string is getting closer and closer and closer to being fully vertical. So at some point, it'll just be pulling up, and that would be at x equals 0. So we have to understand that the string is doing the most amount of work from L to L over 2, then L over 2 to 0. Because from here, ftx is going to decrease. And because work is proportional to force, right, then less force, less work. So let's write that out. So we're going to say So from L to all over 2 compared to, okay. So more work. We're going to say more work. Oh, more work as FTX is greater overall on this interval as compared to the other because, sorry, my voice, I feel stupid, because, let's say, sorry, it's my, you heard me blowing into my mic, that's just me breathing, because theta was, I guess you could say, because theta was greater on average over this interval. Greater force, more work. And there's that one. So let's see this. Okay. Sorry, 1 second. Just gotta check if I actually got that right because I'm doubting myself right now. I swear I did do that right. Okay, yeah, never mind. So cart 1 of mass M1 is held at rest. Oh, this is question 2. Okay. Cart 1 of mass M1 is held at rest above the bottom above the bottom of an incline. Cart 2 has mass M2 where M2 is greater than M1. So this one is greater than this one. Cool. And is at rest at the bottom of the incline at time t equals 0. Cart 1 is released and then travels down the incline and smoothly transitions to the horizontal section. The center of mass of cart 1 moves a vertical distance of h, as shown. At time tc, cart 1 reaches the bottom and immediately collides and sticks to cart 2. After the collision, the two-cart system moves with a constant speed v. Frictional and rotational effects are negligible. Cool. During the collision, is the impulse on cart 1 from cart 2 greater than or equal to the magnitude of the impulse? Greater than or equal to the magnitude of the impulse of cart 2 to cart 1. So let's think here. Both of them have the same final velocity, right? During a collision, the two objects that collide must have equal and opposite impulse. Every action, right, has an equal or opposite reaction. So we're going to say equal to. And we're going to say justify your answer. Newton's third law. So for all action, there is an equal, opposite, we should say, and reaction. So for every action, let's say for every action force, reaction force. Therefore, J1, 2 equals J2 on 1. Right? Where J is impulse. And now you can also just think about this like logically. The impulse that it'll take to bring this cart up to speed v has to equal the impulse that it'll take this cart to slow down to speed v, right? That's just a property of impulse. Like there's equal and opposite impulse during a collision, right? So let's see. On the following axes, draw graphs of the magnitude of momentum of draw graphs of the magnitude of the momentum of each cart as a function of time t, before and after the collision. Before and after TC. So TC is when they collide. Okay, cool. The collision occurs in a negligible amount of time. The grid lines, so instantaneously, basically. The grid lines on each graph are drawn to the same scale. So we have to think P equals mv. So let's think about cart 1 to draw this graph. So cart 1, while it's going down here, it has a constant acceleration down. And we remember from our kinematics, if we have a constant acceleration, the velocity graph will look something like linear, right? So the velocity for cart 1 when it's going down that incline before it collides looks something like that, meaning that the momentum has to look the same, just scaled up by a little bit more. So we're gonna draw it like that. So it has to be linear is my point. That's all that matters, right? So like this. I should just like that. This bothers me. Like that. Cool. But now when it collides instantaneously, it slows down to a different speed, right? So it's going to jump down here. It's going to lose some of momentum and go that way. So it'll chop that way. And now we need to think about cart 2. So cart 2, up until the collision, is not moving. So that's easy. It has no velocity, has no momentum. But it has to jump up, right? It has to jump up to a final velocity. But let's think about this. Is it going to jump up to... Sorry, it has to jump up to its new momentum. Does it jump up to the same momentum? No, it doesn't jump up to the same momentum. The two carts have different masses where they told us specifically M2 is greater than M1, but they move with the same speed after they collide, meaning P2 has to be greater than P1 because M1 is less than M2, right? But they have the same velocity. So you can also think about conservation of momentum. If I lose this bar of momentum here, right? Well, if I lose this amount of momentum here, then I have to gain that amount of momentum here because there's no external force acting on the system, only an internal impulse. So there's my momentum, right? Oh, wait. I just said momentum of cart 2 has to be... Oh, okay. Sorry, guys. The momentum of cart 2 does have to be greater, so we'll draw it like this. And yeah, there is conservation of momentum. So wherever we have to make sure momentum is conserved. So it'll look more like that. So there we go. That's conservation of momentum, and this is way easier. So that's how your graphs want to look. You want to make sure cart 2's momentum is greater than cart's 1 because the mass M2 is greater than M1. There we go. Show that the velocity v of the two-cart system after the collision is given by the equation this. Okay, easy. So let's start by finding the velocity of cart 1 before the collision. So we'll call that v1 naught. So we're going to find v1 naught. So we're going to say, this is just general, we'll say conservation of energy. So UG initial has to go to kinetic of cart 1 because it changed by vertical height h, right? So the initial gravitational potential is mg times that h. So m1gh has to equal 1/2. Well, it's still the same cart. They haven't collided or stuck to each other yet. 1/2 m1 and then v1 naught squared. So these m1s cancel and we get v1 naught equals square root 2gh. Simple enough. Second part, conservation of momentum. So this was, I forgot to say, momentum is conserved because there's no external net force. Also, when it says sticks to, that's telling you it's an inelastic collision, meaning momentum is conserved. Kinetic energy is not, but momentum is conserved. So now we're going to use the conservation of momentum. We'll say P final has to equal P initial. And our P initial was M1, because it's only cart 1 moving, and V1 naught, which was 2GH, which we just solved for. Then after they stick together, they're moving as a system, the two carts. So we'll add the masses. And the reason why I didn't include cart 2 on this side of the equation was because cart 2 had a momentum of 0, because cart 2 would have been m2 times 0, which is the velocity of cart 2. It's not moving, no momentum, so I didn't include it, because there was no point, right? So let's get back to it. So m1 plus m2 plus the final velocity of the two carts, which we'll call v, right? So that's the conservation of momentum equation set up. These two move as a system, and they have the same common velocity. So now I can solve for that. We'll say m1 square root 2g h divided by m1 plus m2 has to equal v. Now, if I rearrange this a little bit, you can see that you can separate the square roots. They wrote it a really wacky way. I don't know why they wrote it like this, but this is also equal to v. So there's your final answer. Easy enough. And there you go. Let's move on to the next part of the question. A group of students use the setup to perform an experiment. They measure the mass of cart 1 to be 0.25 kilograms. The mass of cart 2 is unknown. The students perform several trials, and in each trial, cart 1 is released from a different height h, and the final velocity of the two-cart system is measured. So the final velocity of the two-cart system. Okay, the students make a graph v as a function of square root h shown below. So draw a line of best fit that to represent the data points shown. Okay, so at this point you just get your ruler out. I'm gonna call this my line of best fit. That's interesting that it went through 0, 0, whatever. So now that I've drawn my line of best fit, use your best fit line to calculate the mass of cart 2. Usually with these linearization problems, you're just always gonna pick 2 points, so I'll just do that now. So 0, 0 is my first point. And don't pick a data point that's already shown on the graph. So I'm not going to pick that one. Rather, I'm going to pick, here's like the middle. Where's the middle? I'm going to pick this one. So I'm just going to guesstimate. I'm going to say like, here's the middle. And this point is in like maybe the middle of the middle. So the middle was 1.1. The middle of 1.1 and 1 would be 1.05. So that point can be 1.05 comma 1.8. Was it 1.8? Yeah, 1.8. 1.8. So there's my 2 data points that I'm going to pick. So use the best fit line to calculate the mass of cart 2. Okay. So let's bring back that equation. So V equals square root 2g. Was it square root 2g? I think it was. Yeah. Oh my gosh. M1 plus M2 square root h. Oh, now I see why they arranged it that way. So what they want you to realize is that this is in the form of y, right, equals m. Oh, that's a weird m x, because square root h was our dependent variable and v was what we were measuring. So now at this point, you're going to indicate slope has to equal the square root of 2g, and they want this statement. Like they want to make sure you know what corresponds to slope. Slope equals that. So if I wanted to solve for M2, let's just do a little bit of algebra, right? Let's do slope divided by square root 2g equals M1 over M1 plus M2. Okay, let's flip this upside down. So I can have M2 on the top. So I'll say square root 2g divided by slope equals M1 plus M2 over M1. Multiply M1 so I can get this M2 by itself. So square root 2g divided by slope times M1, right, equals M1 plus M2. Now I just subtract M1 to get M2. So I'll say M2 equals, what was it? Okay, square root 2g times M1 over slope minus M1. Oh, that's M2. M1. And there's our there's M2. So we'll just first we're gonna find the slope. Right? So because we have all of the other values. So slope has to equal the change in velocity over the change in the square root of h, right? And that has to be equal to the 2 points 1.8. So rise minus 0 over run, which is 1.05, minus 0. Let's say 1.8 divided by, this is where Desmos comes in. So this is our slope, 1.7143. Now let's just plug in our numbers in order to find M2. So let's say M2 equals square root of 2 times 9.81. Mass M1 was what? 0.25? 0.25 divided by 1.714 minus 0.25, which is roughly equal to square root 2 times 9.81, because that's gravity, times 0.25. Yeah, that entire thing divided by 1.7143 minus 0.25, roughly equal to 0.396 kilograms. So that's the mass M2, done. After the experiment, the students use a balance to measure the mass of part 2 and find it to be less than what it was determined in part D. So they find the balance and they find that it's less than. So we overestimated the mass somehow. So let's figure that out. To explain this discrepancy, the student proposes that the mass of cart 1 was incorrectly measured at the beginning of the experiment. The students measure the mass of cart 1 again and record a new value, m1 prime. So should the students expect that m1 prime will be greater than 0.25, less than, or equal to 0.25? So these are 3 options. So let's think about it. This equation that we derived, we're going to use it now. So if I decrease m1, overall, that'll decrease this, but it'll also decrease what we're subtracting by. So that's going to be a little bit difficult. But actually, if we decrease what we're subtracting, that's difficult. It's difficult to think about. But I think overall, if we think about it in terms of energy, which would be up here, if we decrease m1, it'll still have the same initial velocity when it's going down, but it'll have less momentum. So it'll have less final velocity because the final velocity, like we showed up here, is dependent on the mass m1. So if overall we have less final velocity, then that means the slope would be less. And if the slope was less, then the mass of cart 2 would be even bigger, so that won't work. So that means the mass of cart 1 had to be greater than. Because if the mass of cart 1 was greater than, right, that'll increase this, and that will, m1 prime, not m1 prime, m1 prime shouldn't be greater than. m1 prime should be, I think, less than, right? Because if m1 prime was less than 0.25 kilograms, the one we used here, if I were to decrease this by let's say 0.20, overall that will decrease our mass, right? Meaning that the mass of cart 2 would be less than what was determined in part D. And that would account for the discrepancy, right? That would bring it back to its actual value. So the derived equation square root 2g times m1 divided by slope. Oh, that's thinking that the slope will be the same. But will it be the same? I don't care. Assuming slope is the same. Because it only depends on the final velocity and the 2gh, but the final velocity is dependent on m1. This is a difficult question, you guys. This has been a while since I've done this. But it is right. So we're gonna think. Oh, okay. Oh, forgive my confusion, you guys. So m1 prime has to be less than 0.025. If there's less mass for cart 2, it says, and find it to be less than what was determined in part D. If there's less mass for cart 2, that means there has to be less momentum overall. Less momentum, by conservation of momentum, means that the initial momentum had to be less. If final momentum is less, then the initial momentum had to be less, meaning m1 is smaller. So because m2 actual was less, P final had to be less, and therefore P initial also had to be less. And since P initial is proportional to m1 V final, and V is always, oh, that's a really bad always, is dependent, I'll just say dependent, only on square root 2gh, not m1. m1 must, forgive my handwriting, be less. So I hope that makes sense, because if the mass they measured was smaller, that means there was less momentum at the end, meaning there was less initial momentum because momentum was conserved. And if there's less initial momentum, then the mass m1 had to be less. Next question. Ooh, I like this one. I remember this one. A solid uniform disk is supported by a vertical stand. The disk is able to rotate with negligible friction about an axle that passes through the center of a disk. Of the disk. Okay, cool. The mass and radius of the disk are given by md and r, respectively. The rotational inertia of the disk is id equals md r squared. A string of negligible mass is draped over the disk and attached to the top of the disk at point P. One end of the string is connected to an unstretched ideal spring of spring constant K, which is fixed to the ground as shown in figure 1. Okay, cool. A block of mass MB is then attached to the spring on the right side of the disk. Okay, so here's MB. I'll just write that. MB. To the right side on the disk, the block is slowly lowered until the spring block system reaches equilibrium, as shown in figure 2. So here's equilibrium. Okay. In this equilibrium position, the disk has rotated clockwise a small angle theta. Cool. Give all algebraic answers in terms of md, r, k, and theta. Okay, cool. Derive an expression for the mass mb of the block. Okay, that seems pretty easy. All we have to think about is pretty much torque. We're going to think about torque. So we're going to say the sum torques on the disk has to equal 0, right? So what's the torques that's being provided? The torque that's currently being provided by the stretch spring has to be, what's it called? It has to be a positive torque, because right hand rule, that spring force, when the stretch spring is connected to the spring force is equal to the tension in the string, because it's in equilibrium, right? This thing is not moving, so the force here has to equal the force there. So I'll just call that Ft. I'll just call that Fk. So I'll say the torque provided by the spring force is positive, right? Minus the torque provided by the block's tension, which is negative using right hand rule, radius cross force, which is down. And also, if it's clockwise, that's a negative torque. So I'll just declare that now. Clockwise is negative torque, counterclockwise is positive torque. That's really bad. Counterclockwise is better. So let's say sum torques equals 0, which is equal to the torque due to the spring force minus the torque due to the gravity of the block. So that means we can equate these two torques. So the torque due to the spring force has to equal the torque due to the gravity from the block, the gravitational force from the block. And now we'll say the radius cross the spring force has to equal radius cross the gravitational force from the block, FGB. And they're both exerted at this point, which is r away. So we'll rewrite this up here as r. Now the spring force is k. The spring force is k, kx, k delta x, and I'll get to that. I'll get to delta x, which has to be equal to r times, and what was the other one? FGB. Now the mass MB of the block is just MB times G. So this is FGB, right? Just like FG equals MG. That's property of physics. So now R is on both sides. I can cancel that. And now I can say K delta X divided by G equals MB. But we have delta X, and they gave us MD, R, K, and theta. So how do we get delta X? Well, we need to understand that delta X is equal to R theta, right? This is a property of rotation, that what you move translationally is equal to the radius times whatever theta you move in radians. That's just how physics works, right? So we're gonna move that down here. Oh, where'd it go? Uh-oh. Okay, please come down here. It's not working with me. Okay, you know what? I give up. I don't care. Delete. So now I can just change this to kr theta divided by G, because R theta equals delta X, equals the mass of the block. Bam, there's my answer, right? And if you don't believe me, I hope you guys believe me. It's right. That's basically right here. V equals RW. If I change this into just position, x equals R theta. Done. That's how physics works. And math. You can ask your math teacher. Okay. Next question. At time t equals 0, the string on the right side of the disk is cut and the block falls to the ground. On the circle below, which represents the disk, draw and label the forces, not components, that act on the disk after the string is cut and the block is falling to the ground. Each force should be represented by an arrow that starts on and is directed away from the point of application. So the disk has a mass, so that means it has its own force of gravity. FG disk. All right. The spring force, or the tension caused by the spring force, I'll just call it the spring force, exerts a force on this side, right? I'll call it Fs. And since the thing itself, the disk is only rotating, it's not moving up or down translationally, the sum forces on the y have to be balanced. So there has to be a pivot force, kind of a normal pivot force up here, balancing the sum forces on the y out. And then that's it. So derive an expression for the angular acceleration a of the disk immediately after the string is cut. So the reason why they say immediately after the string is cut is because immediately after the string is cut, the spring force is still equal to that tension force. I'm calling it the spring force, but it's really a tension force. At this moment, immediately after it's cut, this tension is still equal to that spring force. But after, it'll become a different type of dynamics problem, which we don't want to worry about. So let's find the initial angular acceleration. Let's use Newton's second law in rotational form. Sum torques equals IA, because we have a torque and we have something that we can express as torque, and we're trying to find angular acceleration, so tau. And the only torque that's provided on this disk, right, is the torque due to the spring force, because these two are at radius equals 0, so there's no torque because the forces are being exerted at the pivot, but this is at a radius r away from the pivot. So it would be torque Fs, and that's a positive torque, so we'll call it positive torque. So the torque Fs, like we said earlier, is R, right? And we said the spring force is K delta X, but we know K delta X is really K R theta, which is equal to, now let's sub in, we forgot to sub in earlier for rotational. Let's sub in for rotational inertia. They said it was 1/2 md r squared. And then move that angular acceleration over here. It's the same thing. I'm just multiplying. Yeah, that's right. So now I see, I'm just going to simplify this, r squared k theta equals 1/2 md r squared. Angular acceleration. See r squared on both sides. I'll cancel. And I'll simplify for angular acceleration. I'll get 2k theta over md equals angular acceleration. Done. Finished. Next question. At time t equals t1, the disk has rotated and point P is again directly above the axle. So where's point P? So here's point P. So it's moved and it's back here again. Cool. Is again directly above the axle. Sketch a graph of the magnitude of the angular velocity of the disk as a function of time t from t equals 0 to t equals 1. So let's realize we know that the angular velocity has to be increasing because there's an angular acceleration. That's just a fact, right? But let's think. Is the angular acceleration constant? And the answer to that question is no. Because when point P was directly above the axle, this spring was unstretched. So here tension is going to get smaller and smaller and smaller, right? Because this string is going to stop like compressing it. And this spring will harmonically oscillate if you really think about it, but you don't have to worry about that. You just have to understand that the angular acceleration is not constant. So angular acceleration dt is not equal to 0, right? It's not a constant. So you're not allowed to treat it like one, right? Because this spring force that's providing the torque is decreasing, right? Because when it hits point P, that torque will equal 0. There will be no torque on that disk. But there was torque up here when it was at point P. So when torque equals 0, angular acceleration has to equal 0. So when torque equals 0, angular acceleration has to equal 0 by Newton's second law, because if this is 0, then this has to be 0, right? Because if you multiply anything by 0, it's 0, which means dw dt equals 0. So we know at this point t1, this has to have some sort of horizontal tangent, right? Making dw dt equals 0. So now we have to ask the question, will this be concave up or will this be concave down? And we know the answer to this question because here it has an undefined slope. It's approaching infinity. And in order to have the horizontal tangent, we need a concave down slope. So this has to be increasing and it has to have that horizontal tangent at that point, right? So that's how we know the difference if it's going to be concave up and concave down. And it can't be linear because we need that horizontal tangent. Once again, this is non-differentiable, but we know that this has to be a continuous function because there's no like piecewise. There's no like, it has to be continuous. And if I explain that bad, please let me know. I would love to explain it. Let's look at this last one. So the disc is adjusted so the support, so that the axle does not pass through the center of the disc. Okay, so on the support, so that the axle does not pass through the center of mass of the disc. The block is again hung on the right side of the disc, and the spring disc block system comes to equilibrium once again, as shown in Figure 3. The axle does not exert a torque on the disc. Okay. For each force on the disc, indicate whether the magnitude of the torque about the axle caused by that force increases, decreases, or stays the same relative to part B. So let's list each one. So the torque due to the spring force, let's actually start with torque due to the force gravity disc on the axle increases. Was 0 before because it was exerted at the pivot. Now it is not. And provides a greater non-zero tau. Cool. The force gravity on the block, well, let's think it's the same because this one had the same force. That's why I didn't think about the force. It's the same force for a bigger radius. Okay, cool. So the force of the gravity on the block has to be, so let's say, so tau, force gravity block increases. Same F, bigger R. Oh, you can call that the R/lever arm. And now you may be thinking, well, this spring force, right? It's the same spring force. Well, not the same. It has a smaller radius, so it has to have a smaller torque, right? Wrong. It's a bigger spring force, and the reason for that being is because when we move this disc, right, the center of mass is now exerting a torque. It wants to pull the disc down, right? The center of mass is where all of the gravity acts, so it wants to pull the disc down because before the pivot, right, was at the center of mass. It didn't have a torque, but now it does. So we have a bigger clockwise torque, and the block has an even bigger clockwise torque because the force of gravity is not changing, and R is even bigger, the lever arm. So in order to keep this at equilibrium, the torque due to the force of the spring, which opposes the clockwise torque, which is because the torque due to the force of spring is this way, this one becomes really, really, right, big. So this one has to become just as big to account for the change. So we'll say the torque due to the force of the spring also increases as to maintain some tau equals 0 since CC since I'll just call it clockwise torques increased, the torque due to the spring force as the only CCW as the only counterclockwise torque must increase to account for the change. Amazing. Cool. And there's the end of the exam. I don't know how long that took me, but it took me what it took me. So thank you guys for sticking with me for another video. We used Desmos a lot last this time, but yeah, I hope you guys enjoyed the video, and I hope I explained everything well. Please let me know. I'd be glad to answer any questions, and yeah, good luck on your guys' exams.